So if we're going to have some kind of transform, like the Laplace transform, we also need an inverse transform for our Laplace transform. This is like being able to undo a derivative once you've done it, or undo an integral, right? So we're going to today talk about the inverse transform of the Laplace transform. So it only makes sense that if we took the Laplace transform of lowercase f of t and it gave us capital F of s, then when we take the inverse Laplace transform of capital F of s, we should get lowercase f of t. If only it was always that simple. A lot of times we don't know what we took the Laplace transform of in order to get some value. So instead we would be given capital F of s to begin with, and then have to work backwards. So we're going to take a look at some common inverse transforms to get us started. So we actually have a theorem that says, hey, here are some common inverse transforms. Whenever you see the inverse Laplace transform of 1 over s, well, that function was 1 to begin with before the Laplace transform was applied to it. If you see the inverse Laplace transform of n factorial over s to the n plus 1, that's t to the n. If you see the inverse transform of 1 over s minus a, that's e to the at. If you take the inverse transform of k over the sum s squared plus k squared, well, that's sine of kt. If you take the inverse transform of s over the sum s squared plus k squared, that's cosine of kt. Taking the inverse transform of k over s squared minus k squared is going to give you the hyperbolic sine of kt. And finally, taking the inverse transform of s over s squared minus k squared is going to give you the hyperbolic cosine of k times t. So let's take a look at an example of how we might be able to use this theorem to help us out. Say I want to take the inverse transform of a function 1 over s squared plus 7. Well, I'm first going to match it to what it looks like the most. So it's going to look like either sine or cosine. That's where I have s squared plus something in my denominator. So the problem is I have a 7 in my denominator and have a 1 in my numerator. Since I'm dealing with k squared in my denominator, I really want whatever I square to get 7 in my denominator. So this is really going to be the same as taking the inverse transform of 1 over s squared plus the thing that I square to get 7 is the square root of 7. So square root of 7 squared. Well, then that tells me that k must be the square root of 7. I can't make s's generate from wherever because s's are my independent variables, but k is a constant. And I can kind of work with constants. Remember in math, we can take things and add 0 and multiply by 1 at our will. All right, so I'm going to multiply by 1. But I'm going to multiply by 1 in a way that I'm multiplying by square root of 7 divided by square root of 7. Now, since the Laplace transform and its inverse is a linear transform, I can pull these things into and out of the Laplace transform since they're constants, and all we're doing really is integrating, differentiating, right? So we're going to pull a square root of 7 in, and we'll see what I really have is 1 over the square root of 7 times the Laplace transform's inverse, so the inverse transform of the square root of 7 divided by the quantity s squared plus the square root of 7 squared. This looks exactly like the sine of kt. That's the inverse transform of k over the sum s squared plus k squared. So this is the sine of square root of 7 times t. So this is going to equal 1 over the square root of 7, what I had sitting out front, times the sine of the square root of 7 times t. And like I said, the inverse transform, it is a linear transform. We used that. We can show it over and over again for constants. We can pull constants in and out as we need to. And it all just works out beautifully. So now let's take a look at another example that doesn't look like any of the inverse transforms in my theorem. So let's take a look at the inverse transform of the quantity negative 2s plus 6 divided by the quantity s squared plus 4. So the first thing that we need to do is we need to do some algebra to make this look like something in our theorem that we can use our theorem for. So the first thing I notice is that there's a plus sign in my numerator, and I know that I can pull fractions apart and make this the first part, so negative 2s over my denominator, plus the second part over my denominator. So I'm going to do that. Now remember, you can pull apart numerators this way, but not denominators. So don't ever pull a denominator apart like that. All right? And now I look at this and I say, okay, so I can't treat them both together, so I'm going to treat them separately. I'll take the inverse transform of each of them using the idea that it's a linear transform. And I'm also allowed to pull out constants. Well, I don't see anything that says anything about a constant times s in a numerator, but I do just see s's, so I'm going to pull a negative 2 out in front of my first term. And with my second term, I have a constant divided by s squared plus 4. Well, I see constants divided by s squared plus something. The thing that's added is always squared. So to get 4, I had 2 squared. And the constant has to be the same as the thing I'm squaring. So I want a 2 as my constant in my numerator. And I know 6 is 3 times 2. So I'm going to pull a 3 out in front and leave 2 in. So I'll take the inverse transform of 2 over s squared plus 4 with a 3 pulled out in front as a constant. And now I have two things that look like what I'm working with. So I have negative 2 as a constant still hanging out, and s over s squared plus 4 looks like cosine of the square root of 4, so cosine of 2t. And then I'm going to add to that 3 as a constant still. And 2 over s squared plus 2 squared looks like sine of 2t. So I'll have 3 sine of 2t. And that will be my inverse transform of negative 2s plus 6 divided by the quantity s squared plus 4. So let's take a minute to ramp it up just a little bit more even. So let's look at the inverse transform of s squared plus 6s plus 9 divided by the quantity s minus 1 times s minus 2 times s plus 4. First off, notice that if I multiplied out my denominator here, I would have s cubed. And I don't have any s cubes in my denominator on any of the things in my theorem. And also I don't have any s squareds in numerators, so I need to do something different. And this is where we get to lean on algebra a little bit more again. So we're actually going to use partial fractions here. So let's do a little bit of side work. So I have the thing that I want to take the inverse transform of. I know I want to use partial fractions. One of the things that kind of cued me into that is, first off, if I multiply out my denominator, I get too high of a power of s, but also it's already factored for me. And that's kind of a key thing to go, I might want to use the idea that it's factored. All right, so we're going to use the idea that it's factored here and say, you know what, I know that this must be some a over s minus 1 plus b over s minus 2 plus c over s plus 4. So then all that's left to do is do some multiplication and some solving. All right, so let's do some multiplying. Remember, I need a common denominator in order to be able to add these. So to get a common denominator, I need to multiply all of these fractions that I've created by the two denominators they don't have. So this is going to equal a times s minus 2 times s plus 4 all over all of the fraction parts put together. So s minus 1, s minus 2, s plus 4. Then I'm going to be taking b and multiplying it times s minus 1 and s plus 4. And I'll be adding to that c times s minus 1 and times s minus 2. So it's great, I've done the work. So now I need to actually multiply this out and put some like terms together. So I'm going to have a times the quantity s squared plus 2s minus 8 plus b times s squared plus 3s minus 4 plus c times s squared minus 3s plus 2. Denominator remaining the same still. And continue, distribute my a, b, and c and put the like terms together. So I have an as squared, I have a bs squared, and I have a cs squared. I have a 2as, I have a 3bs, and a minus 3cs. And I have a minus 8a, minus 4b, and a plus 2c, all to work with. And denominator still the same. So now remember, this was actually equal to s squared plus 6s plus 9 all over those same denominator. So s minus 1 times s minus 2 times s plus 4. So if I multiply by the denominator to clear it out, it clears it out on both sides, so I just don't have to worry about the denominator anymore. Note, we could have done that earlier, so it's up to you when you do that exactly. And I just saved it till now so that we could really see this. What we're wanting to do is set our two numerators equal to each other. And we can chunk up our numerator into our s squared and our constant terms. So we're going to set them equal to each other. So the s squared terms on the left-hand side are going to equal just s squared. So s squared is going to equal as squared plus bs squared plus cs squared. 6s, my s term on the left-hand side, is going to equal 2as plus 3bs minus 3cs. And my constant term on the left-hand side, 9, is going to equal negative 8a minus 4b plus 2c. Dividing everything by s squared on this first equation that I have, I end up with 1 equals a plus b plus c. Dividing everything by s on my second equation, I end up with 6 equals 2a plus 3b minus 3c. And leaving my last equation alone, I have 9 equals negative 8a minus 4b plus 2c. I have 3 equations now, and I need to solve them for the 3 unknowns in them. So I'm not going to go through all of the steps of solving that, but you can solve one for A in terms of B and C, plug it into another, solve for B in terms of C then, and plug it in, and then do all the back substitution. Or you could do some elimination potentially. You can set up a matrix if that's your style. Anything you want to solve this, it's fair game. All right, so I'm going to tell you that when you do, you're going to end up with A equals negative 16 fifths, B equals 25 sixths, and C equals 1 over 30. So now we go back. Remember, that was all of our side work. So now we go back and we plug in a, b, and c into these fractions that we had. So what we're really doing is taking the inverse transform of negative 16/5 divided by s minus 1 plus the inverse transform of 26/6 over s minus 2 plus the inverse transform of 1/30 over s plus 4. Picking that back up down here, I'm going to pull the constants out in front, so I end up with negative 16/5 times the inverse transform of simply 1 over s minus 1 plus 26/6 times the inverse transform of 1 over s minus 2 plus 1 over 30, the inverse transform of 1 over s plus 4. Now, going back and referencing our theorem, 1 over s minus a is what these resemble the most. So that's e to the at. I'm going to just make a side note of that so we can pattern match here a little bit. So 1 over s minus a, in this case a is 1, so this is really negative 16 over 5 e to the 1 times t, or just e to the t. And then we have a 26 over 6 times 1 over s minus 2, a is 2, so we'll have e to the 2t, plus 1 over 30. S plus 4 is the same as s minus the negative 4, so we'll do e to the negative 4 times t. And that's going to be our inverse transform. Partial fractions are going to come up a lot in this, so I highly encourage you to get comfortable with them and get used to working through with them. And you'll find that those algebra skills are going to take you really far.